ऑलरेडी 2 लेक्चर्स गायब हैं। एक में साउंड नहीं है और एक डिलीट हो गया था, और जो डिलीट हुआ मतलब वो अच्छा था, अच्छा वीडियो था वो। सो लेट मी, अगर मैं कह रहा हूं अच्छा था वो, so let's redo vanishing and exploding gradients problem. So vanishing and exploding gradients. So we have talked about this. You see, if I have this neural network, okay, so you basically have this input layer, output layer and hidden layers. We may choose to have 0 hidden layers, but if you have more and more hidden layers, at least we tend to believe that the performance of the machine learning algorithm should increase. Okay. Now, right. So, I will write here, we will also talk about how ReLU helps. Okay. Now, so what was vanishing gradient problem? Yesterday I did it in 2-3 minutes. What is vanishing or exploding gradient problem? As you increase the number of hidden layers, so here you have W1 sitting, here you have W2, all the way until WL, okay, where your output layer is Lth layer. Now, if L is high, so let us say anything greater than 20, this will create problems. If you just keep on stacking these, so it is not that something will go suddenly wrong at 20 and before that everything is fine, that is not the case, but it becomes really worse as you, so this number 20 is arbitrary here, there is no, there is nothing very special about this number 20, but as you keep on increasing this, then the problem worsens. Now, so I will keep this as a matrix, so that means del j by del W1 is a matrix, right. Now, if this is a matrix, so or maybe I can just keep on talking about this one term, let us just talk about that. So, if I have one hidden layer, how will this be written? Del j by del y hat by, so just one hidden layer, that means this is the second layer. So, this is my A2, so A2 del A2 by del Z2 by del A1 del A1 So, these many terms we have, right. Actually, one term is missing here, but since it is differential, this is also fine, there is nothing wrong with this. So, this is what you have just for 2 layers. Now, how will this change if I am talking about a 10 layer network? Del j by del A10 and then so on. So, A corresponding to A and corresponding to Z, you will have 2 terms per layer, A1, Z1, right. So, you will have roughly 2L terms, for which gradients you will have roughly 2L terms for partial derivatives in layer 1, right. Now, if you are talking about, so in the same thing, if I talk about del, so in the same thing, if I talk about, let us say del j by del W 1 1 but 2, how many terms will you have? How many terms you will have? 2 less, right. So, basically 2 less means roughly so how many partial derivative terms you will have? As many as, so twice of as many as you are far from the output layer, right, roughly that much. So, of the order of 2 to the L, I mean not 2 to the L, but 2L. How far are you from output layer? So, as you go closer towards output layer, the number of terms will decrease. Now, the issue that we had was this. So, let us say assume, so I will take 100 layers. So, let us say you have del j by del W 1 1 1. So, I will have del j by del A100 because I am talking about 100 layers. What will be the term here? What will be the term here now? Del A 100 by del Z 100 what comes next? A 99 all the way until del A1 del Z1 Is this fine with everyone? This should be fine. I mean, there is nothing special. It only looks scary, else it is pretty simple. Okay. Now tell me. So, how does? So let me just draw it somewhere here. Quickly give me the graph of sigmoid. Something like this. Okay, this will be at, this is 1 by 2, 0.5 and then this is upper bounded by 1 and below it is bounded by 0. What will be the gradients of this particular thing for most of the function? when you compute dy by dx for this guy, what will it be for most of the places? So if you just leave out this region which is finitely many, sorry, not finite. So if you leave out this region, right, this is, I mean, apart from this region, everywhere else you can see derivative is close to 0. In fact, you take z mod z greater than 10 and you will see this is already flat. The value is either close to 1 or close to 0. Okay. Now, so wherever these terms, where are these guys being differentiated? By, so we have for every term, for every layer we have, every neuron must be doing two things. What are they? Compute linear. So it will do linear computation and it will also do non-linear, yani ki activation. Okay. So what happens if I take sigmoid as activation? Most of the places it is 0. So these terms, which terms will be bad? Ab batao mere ko, I don't know. Half of them? By half of them will be bad. Why? Because in half of them you are taking derivatives of non-linearity. So half of the derivatives will have, with very high probability, derivatives close to 0. Okay. So this is going to get worse as the number of layers increase. On the other hand, we will talk about Relu-Rao, not right now, maybe 5 minutes later. So this is fine, right? Now, if you have these numbers that are too small, what will happen? So if a lot of these terms are less than 1, what will happen? Del j by del w11 is 0. And why is this bad? Slow update. Who said slow update? Right. So that's right. Slow update. In fact, no update. But should updates have been there? Update should have been there. Now, so for a second I'll pause here. I'll say if a lot of these terms are greater than 1, then what happens? Gradient explodes. So basically grads, they go to infinity, let's say. Okay. Now, how can I solve this problem? There is just 2 lines of code for this, which is if grades are greater than 100, then grades are 100. That's it. So if it exceeds beyond a region that you think it should not go, right, you just clip it there. So this is called gradient clipping. So in almost all the, in all the cases where you suffer from exploding gradient problem, just do gradient clipping and this works like a charm. You don't really have problems with exploding gradient problems. Problem is vanishing gradients. Why? Why are vanishing gradients a problem? Why can't I clip this one? What is clipping? So this you can do with exploding gradients. How can you do the same with these gradients? You will have to set a limit that if my gradients go lesser than whatever value, then you have to. But then there is an inherent problem with this approach. Why? You want these guys to go to 0. That's what gradient descent is doing. You want these guys to go to 0. They are going 0 because of some other bizarre reason, right? They were supposed to go to 0 when, so they were supposed to go to 0 at minima, maxima, right, plateaus, saddle points, so they were supposed to go to zeros here, and these are good surfaces, we are fine. So if your surface becomes flat, gradients will be 0, right? If your surface becomes minima at 1, gradients will be 0, maxima gradients will be 0, but here gradients are becoming 0 for some other reason. What will happen to learning? There will be no learning for these parameters in this case, because these guys will not be updated, right? As you go towards the output layer, will those guys be updated? As you go closer towards the output layer, vanishing gradients problem will not be as big as here. So those that are closer to output layer, there will be updates, and there will be no updates those that are closer to input layer. So you might have added 1000 layers, but we know, or maybe you have added 100 layers, but let us say whatever, first n are not being updated at all. This is actually worse than having lesser number of layers, because you will initialize parameters randomly. So you have a random network sitting there, right, that is giving you outputs, not learning anything from your data. So that network is not going to do anything good for you. Does this make sense? So then what do we do with these things? How do we solve this? It turns out we don't know. Okay, we don't know how to solve this. So there are again heuristics. So for example, from whatever little I know, Hinton's paper into the LXNet paper, right? It introduced a lot of ideas. So two papers are not, I mean at least two papers are not just papers. One is by Hinton et al, by Alex et al in LXNet, when this deep learning boom actually started, right? They introduced a lot of ideas that were not new, but at once they were tested on such a huge data for the first time, right? There were normalization, there were this ReLU. So they used ReLU. Before then, until then, what you were using was sigmoid. Okay. So problem with sigmoid we have seen, at almost all the places gradients will be 0. But the same problem is there with ReLU as well, but not at almost all the points, but only half of the points. It's not some, half of the points, right? If I can say so, because in the end both are uncountable sets, so you can't really say much. But so right, so what we are trying to say here is, if you replace sigmoid by this ReLU, what happens? For all positive numbers, I have gradient equal to 1, right? Gradient is 1, this is line y equal to x. So those 50 terms that were creating problem for me, those that were becoming less than 1, they suddenly become equal to 1, provided I am in this region. If I am in this region, those are still 0. But is this better than this, which was almost 0 everywhere? Right? So this turns out to be better than this one. Also, this non-linearity itself is better to handle. This was in some sense much more complex non-linearity compared to this one, because this is piecewise linear, this is just in some sense two-way linear. So this function is non-linear, but it is as linear as it could be. You can't have a non-linear function which is simpler than this one, right? So those where you are taking gradients of non-linearity, those terms will become much simpler, gradients will be 1, easy to handle in your back propagation, so things improve if you just remove sigmoid, if you just remove sigmoid in hidden layers and replace it by ReLU. Now from whatever I know, until now it has been very difficult to displace ReLU. So other variants of ReLU have come. For example, you will see leaky ReLU. So leaky ReLU will be this. Now you can answer me, why do we have leaky ReLU like this, where this slope is, so this is also piecewise linear, has all the good properties of ReLU, but has one more good property, which is, if you see, gradients are not 0. So actually anywhere gradients are not 0, and this seems to improve, but in practice it doesn't turn out to be so. Okay. So in practice what turns out is, and even neuroscientists claim that this happens in our brain as well, which is either neuron will fire or it will not fire. So this is equivalent to having a ReLU. So for all negative electrical signals you will not fire, for all positive signals you will fire, right? So what is this essentially doing? If you have ReLU in your hidden layer, if the non-linear term, if the linear term turns out to be positive, this neuron will be active, will fire. If the terms are negative, this neuron will be not active, will not fire. Okay, because it's, what will be its output? 0. Right? When you take ReLU of a number, either the number will be same or it will be 0. So you see, you have introduced a very simple non-linearity. You can't do better than this. And that actually helps not just in managing layers, but also in managing vanishing gradient problem. Now this was leaky ReLU. How was that GeLU? Now there is a problem with this particular activation function. What is that? At 0 it is not differentiable, right? So you improve this by doing things like GeLU, which are something like this. So they bypass this 0 region. This is differentiable everywhere, and ChatGPT kind of LLMs, they use GeLU, not ReLU, not leaky ReLU. Okay, but again they are just ReLUs. You just have this region where gradients are actually much smoother, nicer. Any questions on this? So I'll repeat my question. Why is vanishing gradient a problem? And why is exploding gradient, why can we have such a simple and elegant solution for exploding gradients but not for vanishing gradients? Because you want gradients to go to 0 and they are going to 0 for some other reason other than where you are on the surface. Okay. So these were considered to be a good solution to this problem, but we will come to that later. But RNNs suffer from this problem a lot. Our deep feed forward neural networks will not suffer with vanishing gradients that much. We will see RNNs, particularly that are used for language, they suffer from this a lot. And then you do not do RNNs, you actually do LSTMs that are much better. But then transformer paper actually got rid of RNNs. Okay. But so I will just mention there is this paper ResNet, right. So ResNets are the best way to mitigate this problem. Okay. And we will come to it when we start CNNs in our next class. So next class will be after midterm and we will start with CNNs in that case. So I think all the basics that are required, or at least a lot of basics that are required, are done. Right. So this is done. Now any questions that you might have in this? Right. So let us talk about just one more thing. What are hyperparameters? See, these two, three things you will see everywhere in your machine learning models. So you will need to build models, of course. Second, your models will always suffer from overfitting. If they don't, you are doing something wrong, right? So you have to make them overfit first and then use regularization to generalize well. So if your models don't overfit in the initial stages, then there is something wrong with our approach itself. Okay. So we must overfit and then use regularization next.
If any one of us are building a model, so do you have kind of any particular prescription that we have to follow these many layers?
Can anyone help me with this? How do I decide on the number of layers? So if you had not asked this question maybe for 5 minutes, I had written hyperparameters. So can anyone help me? So he is right, it's your choice how many layers you want to have. So what are hyperparameters now? We have talked a lot about training now. Okay, what are hyperparameters? So help me write some of the hyperparameters. Number of layers, number of neurons in a layer, yes, what else? Learning rate, what else? What else? Can you help me list more hyperparameters? Beta. So momentum term beta 1, RMS prop term beta 2, what else? Basic, huh? Batch size. So basically, let us keep it simple by saying, no, number of epochs is not as such. I mean, at least we don't count them here. Yes, at least I don't know. Okay. Yes. So batch size. Anything that is a variable and is, well, actually number of epochs will also become a hyperparameter because 1 choose karte ho ki 10 choose karte ho, that makes a difference. So anything that is a variable and is not W or B is a hyperparameter. हाँ? कर्नल साइज, कर्नल क्या होता है? क्या बोल रहे हो? So anything that is a variable, right, but is not W or B. Now what are W or B called? Okay. So these things are my hyperparameters, these are things my learnable parameters. Now learnable parameters, the number of learnable parameters that we are talking so much about, that I am also saying I will ask a question in midterm, right? So learnable parameters depend on hyperparameters, because hyperparameters will tell you how many layers are there, that will eventually dictate how many learnable parameters you will have. Neurons in a layer will also dictate the number of parameters. So these three are some of the most important hyperparameters. Okay. Now the most important being this one. Now how do you decide on the number of layers? Choice, right? But can that choice be arbitrary? Yes. Tell me, can that be arbitrary? Anyone else? So, to begin with, it is arbitrary. But as you write more and more such models, you will know, so it won't be arbitrary anymore, right? You will always take an educated guess. So for number of layers, it has to be an educated guess. Similarly for number of neurons in a layer. Learning rate you have to carefully choose. So even your educated guess cannot start with 20, 100, right? Don't guess and keep it 0.03, okay? And then later decide if this was fine or not. Whether you need to increase, decrease. How will you decide whether you need to increase or decrease this? Depending on what? See, you as a machine learning engineer, you have access to only one plot, which is J versus epochs or training iterations. Now, if you have something like this, what will you infer? I should probably increase my learning rate so that I go something like this. Okay. Now, if you go something like this or something like this, decrease because you are probably overshooting and so on. Okay. Right. So, how do you decide the number of layers? You make an educated guess and that will come with experience. So, how many number of neurons in a layer? So, there is nothing that says तुम्हें तो नया बन जाता है यार. Now you educated? So अब मैं क्या बोलने वाला था? क्या पढ़ के आया था मैं यहाँ पे? Right. So you have n input. There is nothing in the literature that says you can't have more than n neurons in the first hidden layer, or there is nothing that says that the number of neurons in lth layer has to be lesser than L minus 1th layer, but you still follow it for almost all the models, right? So there are so many things that math does not forbid. Mathematicians will come and say ReLU is as good as sigmoid in nonlinearity, right? But those who are building models will say, tum karo, we are going to use ReLU, right? Mathematicians are studying stochastic gradient descent with replacement. Computer scientists are saying, see, I don't want to replace, I will simply shuffle my training data set once randomly and then give it sequentially. Okay? So when you are feeding it sequentially, you are not actually replacing things, right? So if you are replacing, what will happen? I have my m training examples, I pick one, train on that, put it back, again randomly pick one. What is the probability that this same number will be picked in the next iteration as well? It is still 1 by m. But when you randomly shuffle it and put it, so you are doing it without replacements, right? So you will see papers about with replacement, but you will see practitioners using without replacement. So again, no educated guesses on nonlinearity. See what people are doing. People are using ReLU, just go ahead with ReLU, right? This one, what happens here? How will you decide how many neurons will be here? There are no guesses here. So if you have yes no kind of answer, then you will have just one. So it's a binary classification problem. If you have more than 2 classes, then you will have softmax here, right? And in fact, sigmoid is just a special case of softmax. So softmax reduces to sigmoid when you have just 2 classes. Okay. Now let me see your consent. So there are things like batch norm, layer norm, and maybe we'll do this when we require them. For example, when we'll come to transformers, we'll do that. But transformers तक आने के लिए we have to go really fast. I have to do CNNs in between. CNNs में मान लो महीना भर. Then we will have RNNs, and then RNNs में we'll do word to vec, RNNs, LSTMs, and then we'll come to transformers. Right? So we have a long journey ahead. Chalo, thank you. That's it for today.